All right, friends and neighbors, time now for another networking video. And in this one, we're going to chat a little bit about the network time protocol. And this sort of goes in with all of our discussions on latency and jitter and iPerf and ping and all of those kinds of things that we've been looking at. And so we're on our way to yet another protocol, one that's an improvement on this one. But right now, we're going to talk about the network time protocol. Now, to get us started, did you ever wonder how your computer keeps track of the time? Now, it might be that you set the time when you first do your build, and then it keeps it forever, because computers are perfect like that. Or there might be something else involved. So when we do this and we type in something like, well, what time is it? And the computer tells us, or we look in the sys tray, or we do something like this, and the computer tells us, how does it know to do that? And it turns out that we have a network time protocol that we can use to tell us what time it is and to keep ourselves in sync with either the rest of the world or our organization. Now, also a part of this discussion is, if you're going to maintain accurate time synchronization, as we've talked about in latency, right? When you're trying to measure something, you don't know what the other side's clock is. You don't know what the delay is between you and them, right? We're sending something across a network, and there are routers and switches and latency and packet loss and queuing problems. There's just all kinds of things that create differences in arrival time or latency along the pathway. So how do we account for the delay? And this is where we get into something that might be a race condition, right? So we think we know what time it is. We might even ask other folks, several folks, what time it is, and they're all going to give me an answer. And what answer gets to me first is dependent upon network conditions and how far away they might be. Now, for a particular process, sometimes packet order synchronization is critically important. I mean, think about financial transactions, anything that has a latency sensitive component to it, telemetry of any kind. So these things are really, really dependent on accurate timestamps. And so what we're going to do is put time servers on the network. And in a perfect world, we have several time servers and several time servers that are not very far away. And these time servers are going to do what? They're going to tell us, well, what time it is. Now, since we've been talking about latency and measuring latency, this note from Cisco is kind of important. It provides accuracies typically less than a millisecond on LANs and up to a few milliseconds on WANs. Clearly, that puts us in that range that we were talking about, where we're, at 10 to the minus 3 to maybe 10 to the minus 4 seconds in accuracy. And most of the time, that's okay, but maybe for whatever we're doing, it might not be. Maybe we need a little more precision. Now, at the heart of the system, we have something called the system clock. And so you might have asked yourself, well, if a server is telling me what time it is, who tells the server what time it is? And it turns out that at Greenwich Mean Time, there are nuclear powered clocks. And so the clocks are based on the decay of radioactive elements to help them keep track of time. That is the half-life of certain elements. And so it is what we call the Universal Coordinated Time, or UTC, also GMT. Now, from that time, we start distributing the time out. And so that's why when we start setting time, we're also we're always talking about UTC or GMT minus or plus a certain number of hours. Now, if you get really, really interested in this, you can take a look at all of the time sources on the web. It's something that you can sort of really go down the rabbit hole on, because the history of our desire to know time goes back hundreds and hundreds of years, all the way back to the search for accurate measurements in terms of longitude, but also time schedules and train schedules and time zones. And now we've got time projects that are on the web, and of course we've got things like this, ntp.org, and the public and private NTP servers that are out there. Now, it's not uncommon for an organization to run its own time server, but what we want is time servers that are close to us to have a more accurate time. And then, of course, we have to ask ourselves, How are those servers being told the time? How accurate is that message from the upstream servers? Now here is a packet list, right? If I just was opening Wireshark and I might look for NTP specifically, there's a couple things that we can get from this. So we can see that they're periodic. We can see that it's port 123 and so on. But how might you do it if you were after it? If you just start capturing, sometimes machines generate NTP traffic and sometimes they don't. If you can tell them to go out and get packets, or if you can say, well, I want to set up a regular polling time, then you can get them that way. But here's a way that you could do it on your own machine. So if you go to your control panel, you can see that one of the things we have here is time and language. Maybe I'll expand this a little bit. And here's one called date time. Now you can see, okay, it's got our, our daylight savings time and our time zone and all of that. You can see where I am if you want to come visit. But now if I say, well, we've got a sync now button. Oh, what does that do? Well, now what I've asked it to do is actually go out and query time servers. So let's see what that looks like. I happen to have Wireshark running, and we can see that I just generated these packets. I can see I've had Wireshark running for a little while, but these are the ones that I just generated, and there is our network time packet. And so this is actually the response. Let's look at the one that I sent out. So this is the client side, right? And then I send out my queries. Please tell me what time it is, and here is some reference timestamps that I'm using. And so this is on my side, what I think it is. And so the idea is that the two ends of the conversation are trying to get an idea of what the delay is in the conversation and what their own local clocks indicate. We can all see a couple things, right? We've got that it's UDP, there's our port 123, and that we're using version 3. Okay. We'll stop that capture. We don't need that to run anymore. So here's what we see in packets, right? We've got UDP port 123. So that means there's no handshake or anything else associated with NTP. There is a polling time associated with the transaction. And so you can see that they usually go out on a fairly regular basis. Now, some places have the polling seconds or the polling time, really spread out. Now, how far are you away from a server is indicated by the stratum. And it also is an indication of how far the server might be away from GMT or UTC. So the primary stratum, the ones that are closest to UTC or GMT, that's stratum 1. We never want to see anything with stratum 0, that's an error. And as the stratum goes up, that means the farther away you are from the original information, and so the accuracy tends to go down. And then we synchronize ourselves with a device that's already been synchronized. So when we want to find out what time it is, we want to make sure that the source for that time has also been synchronized. And this is just a graphic that shows, sort of the hierarchy, where these are the nuclear clocks up here at the top, and then stratum 1, 2, 3. It's not uncommon to get answers back from stratum 2s or stratum 3s. So this is just a little closer look at one of the packets that we might have seen. We can see that this is from the client side again. See the version that we're using, the peer polling interval, how often I'm going to ask for this particular question, and then all kinds of data that's used by the two sides to say, here's how we're going to try to figure out what time it is. And so the magic here is that you get a couple of answers, and there's actually an algorithm that's used to combine the times to try to give you an accurate representation of the time based on your latency, the clock sync differences, and the other end's timing stamps. And here's the other side from the server. And the only other thing I'll point out is that the client had a higher stratum, which makes sense, but there is the stratum for this particular server. Now, if we take a little closer look at that packet list, we can see again, it's UDP 123, but in this case, I'm actually talking with two different time servers, right? So I'm trying to get an answer from two different time servers and combine the answers to get a more accurate representation. And if I look at the conversation that I'm having with a particular time server, 67, 18, 187, 11, here is the timestamp right there, 363, whatever our time base is. And then the next time I communicate with that node, it's 491. Well, if you do a little bit of math, that's 128 seconds, and that was the polling interval that we saw in the original packet. Now here's some stuff just for fun, right? There are differences sometimes in how we describe our time zones. So there's Eastern Daylight Time versus Eastern Standard Time. Sometimes in my case, I'll be thinking about something that might be, my time zone is usually -5, but sometimes it's -4, depending on what we're talking about. And then, of course, there's the daylight savings time. And why do we do daylight savings time? And there's actually a movement out there, of course, to remove daylight savings times. And there's actually another movement that says, why don't we get rid of time zones? And if you really want to go down the rabbit hole, go take a look at why we have time zones to begin with. It's very strange to think about life without them, but we have them for a very particular reason. And that reason might not exist anymore. There's another resource for you, timeanddate.com, if you really want to have a little bit of fun with this and spend some time with, that clock that's sitting on the mantle. Well, thanks for watching. Thanks for listening. This has been an intro to the network time protocol and maybe how we get time across the network. And we now understand that its accuracy level is maybe 10 to the -3 or 10 to the -4th. And that gives us an idea of where it is in our accuracy rating or our precision rating. Hey, like and subscribe if I helped, and we'll talk a little bit more about the replacement for this or another version of this called the Precision Time Protocol later on. But as always, no matter what kind of time service you're using, no matter what stratum you're living in, I hope those packets always reach those destinations.